1. A potter believes that 20% of pots break whilst being fired in a kiln. Pots are fired in batches of 25. A. Let X denote the number of broken pots in a batch. Okay, so initially from the statement, we can assume that this is a binomial distribution. Why? Because we're given the number of batches, which is 25, and we're given a probability of pots breaking, so an actual p-value, which is 20%. So instantly, just say n is 25, and the probability is 20%, so 0.20. Okay, so far so good. Now, a batch is selected at random. Using a 10% significance level, we're going to get to the second. Find the critical region for a two-tailed test of the potter's belief. Now, you should state the probability in each tail of your critical region. Alright, so this isn't so bad. Now, all you have to do really is, given as two tails, this means that we should consider, let's say, a bell curve or straight line. Either is fine. Okay? This means that from each tail of the test, if we split this directly in half, we're looking at the edge. If it's 10%, we take half of 10%, which is 5 because it's two-tailed, and we allocate 5% in this region and 5% in this region. Now, if we assume that the middle is 50% because it's symmetrical, that means the first 5% is here, and the last 5% starts at 95. We only want probabilities that are less than 5% or greater than 95%, but you want to be as close as possible to 5. So what do we do? So well, all we do now is look at the binomial distribution table and just look at n equals 25 and p is 0.20 and just find the closest values. That is up to 5% and just above 95%. So let's do it. So here we go. So look at n equals, initially always find n equals 25 and then p equals 0.20 and n equals 25. So we just scan down this column. So up to 5%, so in this case it needs to be no less than 0.05. So yep, this will be the tightest one. So this represents x is 1. So yeah, just to be clear, they also tell you more information. The tabular value is probability that the random variable x is less than or equal to points x. So this means here initially that this x is 1, so at this point it will be x greater than or equal 1, which equals 0.0274. So we're going to keep this down. And the second one, let's go up to 95%. Alright, here we go. So this is just above 9%, and the tabulated value is 8. So it'll be probability x is less than or equal 8, which is 0.9532. Okay, so now all we have to do really is just plot this down. So looking back in the curve, so this means that up to 8, so this notice how it says less than or equal. We want the greater than equal version, so we just basically 1 minus this term and just switch this to a 9, because this goes up to 8, we want 9 onwards. So let me just write this down. So up to here, this is probability x is less than or equal 1 with exact probability of 0.0274. At this point, this is probability x greater than or equal 9. Okay, the left hand side is less than or equal 8, and that is 1 minus this term, so 1 minus 0.9532 minus 0.9532, and that's it. You should be done then. And yep, and this small region represents exactly 0.0468. So ultimately we can say that the actual critical regions, which are the shaded part, lie between everything less than 1, so it will be the number of batches from 0 to 1. So we can 0 less than or equal x less than or equal 1, 2, actually I should just use the word and, because it's only the shade regions. My pen. And from here 9 onwards, so it'll be 9 less than or equal x less than or equal 25, because that's how many it goes up to. And I said this should be the end of solution. That's what we want. We want the values x that fit along this, that are less than 5%, or just over 95%, or the remainder 5%. Okay, here we go. Part B, guys. So the potter aims to reduce the proportion of pots which break in the kiln by increasing the size of the batch fired. He now fires pots in batches of 50. He then chooses a batch at random and discovers that there are 6 pots which broke whilst being fired in the kiln. Okay, just to make a quick note here, from the previous question, we had a binomial distribution of of 25, batches of 25, with a actual proportion of 20% which he believed would break. So we could instantly state that now the distribution changed to for n equals 50, because now there are 50 batches, and the proportion would actually still be 20%. It's not going to be 6 out of 50. Why? Because this is how much he actually discovers. So this is not a rate. This is a rate, okay? This is how much he actually discovers, which is something different. That's going to be probability of finding if this falls in line. So now let's have a look. So test at the 5% levels of significance whether or not there is evidence that increasing the number of pots in a batch has reduced the percentage of pots that break whilst being fired in the kiln. Just to recap, 6 over 50 is the same as 12%. So technically it's under 20%. So we need to check if this statement is actually true. Now, first things first, we need to lay down our hypothesis. So we could say firstly that the initial hypothesis and the alternate hypothesis, we could say that the probability according to our binomial distribution, that the pots that are expected to break were 20%. However, with the new information, we found out that it could be 12%. So we're going to test whether or not the probability that it actually breaks is under 20%. So here we go. That's all we do. The figure's always the same. You're just testing whether this is true or actually less than that. That's all it is. And now to confirm this, we need to test the values they assumed, which was 6. So we're going to follow this lead, the H1, with the same direction. This means the probability that x is less than or equals 6. And then we just, well, refer to the binomial distribution with n equals 50. Anyway, guys, so let's whip out the tables and let's have a look. So going to n equals 50, which is down. So keep going down your tables until you find the right proportions. So here we go, n equals 50. And we're looking at 20%. So let's change to red. Okay, so when n equals 6, so when x equals 6, so this would be probability x is less than or equals 6, we should get exactly 0.11034. Okay, let's write this down. So 0.1034. Now what does this tell us? Well, we only firstly reject the null hypothesis if the p-value, the probability, is less than 5%. If this is the case, this is just like a general rule of thumb, then we reject the null hypothesis. Okay, so in this case, this one is not less than 5%. So we can say there is insufficient evidence, or there is not enough evidence to reject the null hypothesis. So what does this actually tell us? So if we can't reject it, if there's insufficient evidence to actually reject it, that means we're going to accept it. So we're going to assume that the probability remains constant at 20%. So we have to agree with the potter's belief. So that's what it really means. So ultimately, we can say that there is no reason to assume the new beliefs. So we can say whether or not there is evidence that increasing number of pots in the batch is reduced. So all we do is just pretty much say there is no evidence, and then copying that statement again. So there is no evidence that increasing number of pots has reduced the percentage of pots. And that's it, that break. So copy all of this, but replaces with the word no evidence, and we should be good. And just checking the mark scheme always helps. There's various other routes you could take. So they say no evidence that increasing the batch size has reduced the percentage of broken pots. So this is one way of writing it, or you could even say evidence that there is no change. So a company receives telephone calls at random at a mean rate of 2.5 per hour. Okay, first things first, what distribution are we using? So in this case, we're finding the mean rate. So this can only mean the Poisson, because the Poisson distribution only works with the lambda, which represents the mean rate. Okay, so this means that the lambda here is 2.5. And this is x per hour, yeah? Per hour. So that's very important to note. Now, A, find the probability that the company receives at least 4 telephone calls in the next hour. So this implies the probability that x is at least or greater or equal 4 in the next hour with this parameter here. So to use the table directly, we need to rewrite it in the less than or equal form. So to do that, Well, if it's greater than 4, then we can just say the reverse, which is 1 minus x less than equal than 3, because this is 4 onwards, we want 3 backwards. Now doing that, quite easy. So 1 minus. Now all we do is just go to the tables, find x less than equal 3, and remember to follow the lambda. So look at the Poisson, find 2.5, and then go down to 3. And it should be, and even tell you here, this is the tabulated value, less than equal x. So this should be it. So 75, 76. So 75, 76. And that should give us minus 75, 76, 24, 24. So 0.2424. Easy. Now find now part 2. So exactly 3 telephone calls in the next 15 minutes. So this is the probability. Let me change the color pen. That x equals 3 in the next 15 minutes. So this is a new distribution. Notice how the original was per hour. This is 15 minutes, so this is 4 times less. So you would have to divide this by 4 to make it correct. So in your calculator, do 2.5 over 4. This will give us a mean rate of 0.625. So now we have a new distribution, a Poisson with mean 0.625 per 15 minutes. So always note these down. Now this is going to be equal to, so here we have to use a formal definition. The formal definition is always, I can write down here, probability x equals x is going to be e to the minus lambda, which is the parameter, times lambda to the power x over x factorial. In this case, x must be integer because Poisson and binomial only accept integer numbers, yeah? Otherwise a factorial wouldn't work. So now plugging this in, so for x equals 3, we're going to have probability x equals 3, which is equal to e to the minus lambda, which is 0.625, and then times 0.625 to the power 3 over 3 factorial. You should get 0.0218, I believe. Yeah, so I'll go something like that. Okay, here we go, part B. So find to the nearest minute, okay, so when you change that to hours, minutes later, the maximum length of time that the telephone can be left unattended. So that the probability of missing a telephone call is less than 0.1. So this is a bit funny because this is talking about missing a telephone call, so it's actually a reverse statement. So the probability of leaving a call unattended is x equals 0, meaning no calls. But to miss a call as well would be the opposite, be 1 minus this terminology. So 1 minus not picking up the call. So this is going to be a higher probability. And all of this must be less than 0.2. So this would be our statement. We also need a new distribution as well because we're working with time. Let's let the new time variable be t, yeah? Because we want to find out exactly how many hours per t. So t per hours or t per minutes. So it'll be x is a Poisson distribution with mean 2.5 t per hour. So once we work out the t value, we can work out the number of minutes that can be missed. So let's have a go. Okay, hopefully you guys are following me with this one. So let's rewrite the statement, yeah? So what do we have? Yeah, so you could actually, let's just throw this on the other side, yeah? Well, let's keep it like this. So we got 1 minus the probability x equals 0. So using a Poisson distribution, it'll be e to the minus lambda, so e to the minus 2.5 t times lambda, which is 2.5 t to the power 0 over 0 factorial. Okay, and all of this should be 1. So I don't know why that's even there. And all of this would be less than 0.2. Now this is just a case of solving, so we need to make t the subject. So what we could do is plus this to the other side and subtract 0.2. The other side, so we have 1 minus 0.2 is 0.8, less than e to the negative 2.5 t. Taking the natural log on both sides, so we got ln 0.8 is less than ln of this, and that will drop, so it'll be minus 2.5 t. And now inverting the position, so throwing 2.5 t to the other side, so it'll be a positive 2.5 t, because sometimes working inequalities can be messy. And throwing this to the natural log to the right side, it'll be minus ln 0.8. And that's it. Now all you do is simply divide 2.5 across, so you're going to have t is less than minus ln 0.8 over 2.5. Put this in a calculator and you should get 0.0892 .57 hours, and to convert this to minutes, well, just times your result by 60 and you should get the time to be less than 5.355 minutes. 55 minutes. Okay, part C. So the company puts an advert in the local newspaper. So according to this statement, the number of telephone calls received in a randomly selected 2-hour period after the newspaper is published is 10. So let's just write this down here. So this is just a statement, okay? Again, it's not an average. So according to the statement, for a randomly selected 2-hour period, we can assume that the Poisson distribution, if it was 2.5 calls per hour, would be double. So it would be 5 calls per hour. Okay, so that's where we begin. Now, test at the 5% level of significance whether or not the mean rate of telephone calls has increased. Now, we're just looking at 1, okay? And apparently it seems to be far greater than the average rate, which is 5. This paper seems to have at least got 10. So we can test using the distribution tables the probability that x is greater than or equal than 10. Okay, but we also need to state our hypothesis clearly. So before we even do all this, we can even say, let the null hypothesis and the alternative hypothesis be represented by the mean rate equal to 5, or if the mean rate has increased, so it would be greater than 5. Okay, so this is where we're going at. The reason why it's greater than 5 because we're testing whether then the mean rate of course has increased from, let's say, 5 to the published statement of 10. So let's check this out. Let's just go have a look what probability x greater than or equal to 10 is. Well, first things first, because we're using tables, it has to be written in the less than equal form. So if this is 10 or greater, we need 9 or less. So this will be 1 minus 9 or less. Now let's go ahead and look at the tables for Poisson 5 and 9. Okay, let's have a look. So yep, so lambda is 5 over here, perfect, and we're looking for x equals 9. Oof, so it's quite close, isn't it? Alright, so this is what they got. So we're looking at this. So let's have a look. So it'll be 0.9682. So that's what the probability x less than or equal 9 equals. So let's 9682. So it'll be 1 minus 9682. So this already, to me, this already looks less than 5%. So, I mean, I already know what the statement is. So let's have a look. So we got 0.318. Oh God, that would be a fatal error. 0.318, and this is clearly less than 5%. Now, the whole point of this is that when you want to reject a specific null, we need to test whether the p-value is less than 5%. The p-value is the probability value, so it's this. And yes, it's less. So because it's less, we can comfortably say that there is enough evidence. So we always say that there is enough evidence or sufficient evidence to reject the null hypothesis, to reject HO. So if we can reject HO, this implies that we have to accept that this statement is correct, that there is enough evidence to suggest that the mean rate of telephone calls has increased to 10, or at least has increased. That's true enough. And that's it. So make sure you say this statement plus that there is enough evidence that the mean rate of telephone calls has increased. Saying all of this will nab you 2 marks. If you only say this, you get 1. So please make sure you say both if you want the full marks. Anyway, guys, hope this helps, and I'll see you next time. Question 3. Let's check out. So the lifetime x in tens of hours of a battery is modeled by the probability density function. Okay, so here's the PDF. Now, use algebraic integration to find the expected value. Okay, this is very straightforward, yeah? If we know the definition of expected value, I can write over here. Ex, at least in terms of integration, is always the integral from the limits, let's say a to b, of x times fx. Simple as that. That's all it is. It's always this case. So in other words, we just have to multiply x to the density function. So this is going to be equal to the integral. So let's just simplify this, yeah. If you want to integrate this, you can take the constant, so it'll be 1 over 9 for a second. So it'll be the integral from the limits 1 to 4 of all of this times x. So if you multiply this out, so it'll be 4x minus x squared. And then if you times x in front of it, you're going to get exactly 4x squared minus x cubed dx. Alright, so this is the main thing. Now this is quite straightforward, it's very linear. So ignoring the 1 over 9, integrating this, you should get 4x cubed over 3 minus x to the power 4 over 4. And then you just evaluate from 1 to 4. Yeah, and that's really it. And then when you do that, so you got 1 over 9. Firstly, you just plug in 4. So when you plug in 4, what do you get? Minus, and then when you plug in 1, you should get, hold on, 12 I mean. So the final result should be 64 over 3 minus answer times 1 over 9. 9 over 4. So you should get 9 over 4 as your result. Yeah, pretty straightforward actually. That's what you do. Okay guys, here we go. Parts B and C. So as usual, we're given the random variable x in tens of hours with the following property density function. Okay, so it's all copied out here. Now let's evaluate B. So find the property that the random variable x is greater than 2.5. So the only way to do this, firstly, is to use algebraic integration. Why? Because we're working with continuous values. So this is a range. So we need to find the time when x is bigger than 2.5. Well, the only way it goes up to is that we start from 2.5 and it goes all the way up to the limit 4. So that's exactly what we're integrating. So we can say that the solution B is simply going to be the integral of the density function from 2.5 to the highest limit, which is 4, and dx. That's it. So we just pick this value 1 over 9 times x, 4 minus x, and just plug in and solve and just integrate. Very easy. So it's going to be, firstly, because you got one, I'll show you a nice trick. If you got 1 over 9, just whip outside like you did for part A, pop it outside, and you're going to have 2.5 to 4. Simplify this part, so x times 4 minus x would be 4x minus x squared dx. And this part's fine now. So let's do it. So this is going to give us now, so integrating all of this, we should get, so 4x becomes 4x squared over 2. 4 over 2 cancels out, so you get 2x squared minus x cubed over 3. And you're going to evaluate from 2.5 to 4. So yeah, that's all we do. So firstly, plug in 4, find the value, then plug in 2.5, find another value, and you should get 3 over 8. And voila, that's it guys. Hope this helps. And let's move on to the next one. So here we have a radio that runs using 2 of these batteries. Okay, so let's just keep that in mind. So if they're using 2 batteries, it looks like we need to use 2 different probabilities, maybe. So both of which must be working. 2 fully charged batteries are put into the radio. So part C, find the property that the radio will be working after 25 hours use. So one thing to know here, when they say 25 hours use, recall that the random variable x is measured in tens of hours. So this probability for part B, x greater than 2.5, that's measured in 10, so it'll be actually, in reality, this is 25 hours. So in fact, this statement here is the same as x greater than 2.5. And now, because we're using 2 batteries, this means that the solution for part C means we need 2 of them. So probability x greater than 2.5 times probability x greater than 2.5. So we need both of these happening. And well, we know the solution for both. This is 3 over 8, and of course, this is 3 over 8. So multiplying them out, you should get 9 over 64. Very easy problem, very easy. And here we go, the final part, part D. Let's see. So given that the radio is working after 16 hours, so find the probability that the radio will be working after being used for another 9 hours. So first thing to notice is that we're using a given that question. So every time you have a given that question, we know that the probability is going to be on the bottom half of the fraction. And it says after 16 hours. So this is immediately x greater than this variable. One thing to know, we're working in tens of hours. And as you recall from part C, when it said find the property that the radio will be working after 25 hours, This literally meant x greater than 2.5 because of the tens of our system. So literally this means x greater than 1.6. So let's put over here, solution for D. We know firstly that the bottom variable, the given that part, would be x greater than 1.6. So it looks like we need to solve that. Now, for this plus statement, find the property that the radio will be working after being used for another 9 hours. Notice how to use the word another 9 hours. So this literally means after the original 16 plus 9 hours, which is actually 25, which is actually what we did for B and C. However, be very careful here, yeah? We're talking specifically about the radio, meaning the radio requires 2 batteries, meaning we'd only care about this probability, not this one. This is the battery. Okay, so this is actually a common mistake here, a very common mistake, so be very careful. We want the radio, which is 9 over 64. So instantly, this is actually officially written as x greater than 2.5. Now, one thing before I forget to note as well is because we're using radio for both of them, remember they're both radios, we're going to have to square both of them because we need 2 of them, yeah? That's exactly what we did earlier. I know we multiplied both twice, but it's the same by just squaring. And okay, so we know what we have. So the solution to part C, which we already had, was 9 over 64. So this squared was 9 over 64. That's okay. Now let's try and work out this property, x greater than 1.6. Okay, so this is quite fine. Now this is just standard procedure here. You just take the density function, integrate from the limit, so from 1.6 onwards all the way to 4, and you just smash it all in. So let's do it. So 1 over 9 outside, integrate from 1.6 to 4, you should get 4x minus x squared and then dx. Easy. Now, just to get into the standard format before I just give you the pop out on the answers, 4x is 4x squared over 2 or 2x squared, and then this is x cubed over 3, and yeah, 1.6 and 4. Okay. So as per usual, plug in 4 over here and then find the result, and then plug in 1.6 over here and then evaluate all, find the difference and multiply by 1 over 9. You should get 96 over 125. Now this is this probability. To get the squared version, well, let's square this result in our calculator. Yeah? So 96 over 125 squared. Oh god, that's one ugly probability. Well, I'm not going to keep it. I'm just going to write as it is. So it'll be 96 over 125 squared, and then plug in everything in. 9 divided by 64 over the answer. Ooh, you should get about, let's say 4 decimal places, 0.2384. And that's it. Case closed. This is part D for you guys. And I hope this helped. This is kind of a very risky question because they're talking about specifically radios, yeah? So always, be careful what you're trying to find there, yeah? They both need 2 batteries, hence... Okay, guys, here we go. Question 4. So the continuous random variable x is uniformly distributed over this interval, alpha and beta. So this is clearly a uniform distribution with these parameters. Now, given that the mean is 3.5 and the probability that x is greater than 5 is 2/5, let's find out what a and beta is, yeah? So first things first, with these kind of questions, always parameterize, yeah? Always say what the density function is. So fx is always given to be 1 over beta minus alpha. The function fx, the big F, the cumulative one, is always x minus alpha over beta minus alpha. So you just integrate it and you'll get this result. And the last thing is the mean. So one of the more relevant ones is half of the sum of these two. So it's just the midpoint. Because it's uniform, we'll be bang in the center. So beta plus alpha. Okay, easy. So we can actually work out this straight away. But just have a clear idea. For the first one, ex equals 3.5. This means that this part here, ex equals 3.5. So we can easily solve that. So we can say, can I go down? No, not too much. So I can say half beta plus alpha equals 3.5. Times it by 2. You can just say beta plus alpha must equal 7. Okay, so let's consider the second one now. When probability x greater than 5 is 2/5. Okay, so what does this mean? So this means if x greater than 5 is 2/5, this function fx is firstly, what is it equal to? It's equal to property x is less than equal x. This is a formal definition, yeah? If you don't know this, this means that it's accumulating all the way up to x, okay? That's what it means. So, but because we got this side, we need to flip around, so we need to take property x less than equal 5, which would be the other way around, so it would be 3/5. Because if you think about it, all the values of x up to 5 plus all the values of x greater than 5 will give you a whole number. So 2/5, 3/5 seems logical. Now what can we say? So this means this function will be equal to this. So we can say 3/5 will be equal to the fx1 at the point 5, at f5, yeah? So when x is 5, so oh yeah, another formal definition is that f5 means probability x is less than or equal 5, yeah? That's what it is. Also, it might be useful, this is also officially known as a survival function. So the probability of survival. You learn this in more advanced probability, not in what we're doing. And this is the same as probability x is greater than 5. It's just the reverse. If you sum with the cumulative and the survival, you get 1. But yeah, let's get back to the main problem at hand. So this means for part A, 3/5 will equal this at 0.5. So we're going to have 5 minus alpha over beta minus alpha. Oh, and you can see that this is going to be a bit long. So what I'll do for the first equation, or just to make life easy, cross multiply, so times 5 across and beta minus alpha across. We're going to have 3 beta minus alpha equals 5 times these guys, so 25 minus 5 alpha. Now what we could do is make, let's see, let's make a beta subject here. Okay, actually let's make beta subject here. So we're gonna have beta equals 7 minus alpha. So just a case of simultaneous equations, yeah? So plugging this in, we're gonna have, let's expand this, 3 beta minus alpha, 3 alpha equals 25 minus 5 alpha. So 3 times 7 minus alpha, so this would be 21 minus 3 alpha. Minus another 3 alpha, we get minus 6 alpha. Okay, and this is equal to 25 minus 5 alpha. I really need more space, don't I? Okay, let me just get this out of the way. Okay, so continuous equation, so just plusing 6 alpha across and subtracting 5, we should get exactly 1 alpha on the right side, minus 25, we get minus 4. So alpha seems to be minus 4. So if alpha is minus 4, that means beta automatically is 11. Alright, sounds good to me. Okay, part B. So given that probability x less than c is 2/3, find the value of firstly c and then find the probability that x lies between c and 9. Okay, so let's go ahead and tackle the first problem first, yeah? And also let's try and represent this. That's the most important thing. First, notice that this one is again the cumulative distribution function because it's written in the less than form. So so fx is always the same as x less than equal x. This is literally the formal definition, yeah? So in this case, what does this mean? So probability x less than c, which is in this case the same, is going to equal the function at the point c, which we already know is 2/3. Now the function at the point c for uniform distribution is always written like this. It's always c minus alpha over beta minus alpha. Usually it would be x, but this is the uniform distribution definition. Now let's move forward here. So we already know the values of alpha and beta minus alpha. Again, this all equals 2/3, yeah? So what do we say? So let's see. Simplifying this, so we're going to have now c minus alpha, so c plus 4 over beta minus alpha, so 11 minus 4 is 15. This must equal 2/3. Now you just solve to find c. So solving this, let's see, let me just bring this up. Yeah, I got space up. So we can say c must equal, so it will be 2/3 times 15 minus 4. So 2/3 times 15 minus 4, and I get 6. So that bit is done. So c equals 6. So I'm going to use the space up here. So now we're going to find the probability that x lies between c and 9. So we just need to think carefully how to write this. So we can think of this as firstly all the values that lies between C, which is 6, on my right C, between 6 and 9. So let me think. It could be written as, firstly, the property x is less than or equal to 9 minus, so this is all the values up to 9 minus all the values up until 6. The reason why we choose 6 and not 5 is because it's continuous, it includes 6 and bits of 6. So we just want all the values just below 6, literally. But again, continuous doesn't really measure single points. It measures like a range of values. That's why we use it. And this is easy. So this is just literally going to be now the function at the point 9 minus the function at the point 6. We already know what the function 0.6 was. It's 2/3. Now function at point 9, well, it's the same formula. Just plug in 9 for x. Or you know what, let me just make it again the same way. It will just be the cumulative function, so it'll be 9 minus alpha over beta minus alpha minus the 6th version, which is 2/3. So alpha, beta minus alpha, so it'll just be 9 plus 4 over 11 plus 4 minus 2/3. So smash this in your calculator, guys, and we're done. So 13 over 15 minus 2/3. Yep, and I got 1/5. So that means this solution here is 1/5. So I can see the difficulty in these problems. This is all about algebra manipulation, you know. So it's a bit intense. There's a lot of things going on, but as long as you know the formula, you just have to make sure your algebra is on point. And just be careful, guys, yeah? And we'll see you in the next one. Okay, final question of number 4. So a rectangle has a perimeter of 200 centimeters. The length s centimeters on one side of this rectangle is uniformly distributed between 30 and 80. Okay, let's just take a note of that. We can say, oops, not x. We can say that s is uniformly distributed between 30 and 80. Now, find the probability that the length of the shorter side of the rectangle is less than 45. So this is kind of like a bit of arithmetic. I mean, if you're going to find property one side is shorter than the other one, then the other side must be longer to guarantee a perimeter of 200. So let's just have a think about it. If we drew a rectangle right now, and we want to guarantee that the side, let's say is 45, is less than 45, this means this length must be greater than 55. Why? Because we want to have a total perimeter of 200 in the end. These two make 100, so these two must be 100. So whatever this is, this will be the remainder. So effectively, to guarantee this statement, we need to ensure that this probability and this probability both hold to guarantee 200 centimeters. So let's say that. So we can say find the probability that s is less than 45 plus the probability that s is greater than 55 centimeters. We ensure that we're going to have 200 centimeters. Now what is this? So this is just simply the uniform function, the cumulative function. So we can say with the parameters 30 and 80, we can express this one as f45 plus, and this is actually 1 minus f55. Okay, so that's what we have here. This one is easy. This is just 45 minus alpha, which is 30, over beta minus alpha, and then 1 minus, and same thing here. So this would be 55 minus alpha over beta minus alpha. So I'll just make a note there. So that's how it works. And the uniform distribution is given to be 30 to 80. So actually this wasn't too bad. We just have to guarantee these proportions really. Now putting this in a calculator, well, this should give you 3/10. This should give you half. So effectively 3/10 plus 1 minus a half should give us 4/5. And that's it, guys. Here we go, guys. Question 5. So the time taken for a randomly selected person to complete a test is m minutes, where m is normally distributed between 14 and sigma squared. So this is the mean 14 and variance sigma squared. Given that 10% of people take less than 12 minutes, so note this down, to complete the test, find the value of sigma. So first things first, we need to write on what we know. So since we know that the probability that the number of minutes was less than 12, we know that this represented 10% of people. In other words, this can also be written as 0.100 if we looked at the normal distribution table. Now all we have to do firstly is convert this part, the left side, to the standard normal. So that's basically the z part. So we can say z is less than 12 minus the mean, which is 14, over the standard deviation, which is sigma. Okay, and again, this is equal to 0.1000. Now what do you do from here? Well, the problem with this table is that this only records values from 50% onwards, because if you go back to the normal distribution table, we can see that if we look at the probability values, because inside the z is the probability values, is these ones. They start from 0.5 all the way up to 1. So technically we need to find the reverse value, that is the 1 minus value. So if we go back again, in order to work this out, we can also take it like this. If we take 1 minus on both sides, we'll have the same expression, except now this will be 1 minus this, so it'll be 0.9000. And yes, this can be picked up. And the cool property of normal distribution is that if you got 1 minus the probability, and you can put this, cross out 1 minus and put this inside as a negative. So this can be written as the probability that z is less than the negative of 12 minus 14 over sigma equals 0.9000. And yes, this actually works. So if you were to do this, now we can actually equate this to whatever the 0.9000 figure is. So going back to the table, the closest probability to 0.9000, so have a look at this term here. We can see it falls between here, so actually it's close to 1.28. That's very close. So we can say immediately that all of this equals 1.28, about 1.28. And now we just solve this and find sigma. So we can now say, therefore, minus and then 12 minus 14 over sigma must equal 1.28. And now we just have to resolve this. So multiplying sigma across and then times in the minus across, we should have minus 12 plus 14 equals 1.28 sigma. This reduces to 2 equals 1.28 sigma. And simply dividing 1.28 across, and you should get about sigma equals 25 over 16. But it's best to keep the answer as a decimal because we're working in minutes, so we can't really use a fraction. So we can say approximately, well, actually 1.5625 minutes. And that's it, that's part A wrapped up. Okay, part B now. So Graham selects 15 people at random. Find the probability that fewer than 2 of these people will take less than 12 minutes to complete a test. Now, first things first, we know that we have a new sample size of 15. So again, this could be normal or binomial. However, how do we know that this is binomial? One, it's because we're talking about people. We're talking strictly on integer values. Because you can't have 50, you can't afford 2 point something people. We're having specifically 2 people. So we know straight away that this is going to be now a binomial distribution with n equal to 15, but we need to figure out p is. We can ignore this statement. This is just a distribution where we had the m1 from the previous question, which was here, where m was represented as minutes. This is the time taken, and this statement here, less than 12 minutes to complete test. This is the proportion we're talking about. We're talking about 10% of the people. Again, we're talking about people in this case. So now our p-value would actually be 10%. So when you have a question like this, always try and figure out what the proportion is. Now we know it will be 15 and 10% or 0.10. So now we can answer the question. So find probability that fewer than 2 of these people. So probability x is fewer than 2. Now thankfully we have this in our Edexcel binomial table. So this can be rewritten as probability that x is less than or equal than 1. Remember, this represents when x is either 0 or x equals 1, but not 2. So technically it's the same as that. Now all we do is simply go to the binomial table. So open it up over here and simply find when n is 15, go all the way down, and when x was when probability was 10%, so p equals 10, 0.10, and we just find 1. So and actually his answer would simply be 0.590. It's 5490, and that's it. So where is the thing? So this would be equal to 5490. Very straightforward. Just be very careful how to model it as a binomial, not as a normal. And that's it. All done. Part C. So let's have a look. Giovanna takes a random sample of n people. Okay, so instead of the previous one we had 15 people, so now we got n. Using a normal approximation. So this is converting either binomial or partial to normal, but this is likely going to be binomial. The probability that fewer than 9 of these n people from the sample will take less than 12 minutes to complete the test, and that is given to equal 0.3085. Find the number of people. Well, first things first, we're looking at a distribution which features less than 12 minutes. We know this by now. This is the one from the given that statement where we know that 10% of these people take less than 12 minutes. So we know the proportion is 10% or 0.1, 0.10. And because we have a sample of n people now, we can say straight away that this new distribution, let's call it y, we would follow a binomial with firstly n people and 0.10 probability or proportion. Now, how to convert this to a normal is very straightforward. Firstly, all we need is, let's say this. We need to find the mean, which is simply for binomial n times p. And we need the variance, which is simply from binomial n times p times q, or you might see as np times 1 minus p. It's just the leftover. So what do we have here? So this means straight away that mean is going to be n times this, which is 0.1n, and multiplying the next one to find the variance, n times 0.1 times 1 minus 0.1 will give us 0.09n. And that's our literal normal distribution now. So we can finally say that y is now normally distributed with a mean of 0.1n and a variance of 0.09n. The standard deviation would be the square root of that, by the way. So, almost done, guys, almost done. One thing to know, when you're using the normal approximation, notice how the binomial only takes integer values, yeah? So if it said fewer than 9, it could refer to less than equal 8. However, if it's a normal distribution, it's continuous. So fewer than 9 is same as less than equal 9. However, when we take that into account, because we have now probability under binomial, less than 9 is equal to less than or equal 8. For normal approximation, we have to take a continuity error or correction in this case. So it would be, I mean, personally, I always use the midpoint. So I'll say, therefore, under normal approximation, I would say probability that y is less than the midpoint, which is 8.5. The reason why we do this is that we just want to have a safe assumption. Okay, that's really it. So where are we now? So find probability that fewer than 9 of these n people will take less than 12 minutes, blah blah. And we know that this probability equals 0.3085. Equals 0.3085. So we're almost done. Now we just convert this to the usual Z format. So let's have a look. So standard normal, here we come. So it'll be less than 8.5 minus the mean, which is 0.1n, over the standard deviation, so it'll be the square root of the variance. So root 0.09n. And all of this must equal 0.3085. Now you can see where we're coming here. Here we now need to find a certain z value from our table that will make this equal to this probability. Well, as we always know, according to the normal distribution table, so let me just scroll up to it. Right here. Probabilities begin from 0.5 and end to 1. So technically, we need to firstly find the reverse order. So we need to find 1 minus this. Or what we could do is find 1 minus both sides, and then we'll find the other side, the right hand side. So let's have a look. So we can say if you 1 minus both sides, or just stick in a nice negative sign here, this will automatically change this to 1 minus this variable. Literally, that's a nice way. So if you stick a minus sign here, it will be 1 minus this probability, which is equal to 3085, 0.6915. And that's it, guys. All you do now is find this probability on the table and then equate all of this to that. So going back to that table, where did I put it? 6915. Oof, takes a lot of work, you know. So equals 0.50. 0.5, that's perfect actually. Nice. Now you just solve for n. Alright, so I just need a little breather here. So now we need to equate all of this 0.50, so let's do it. So we can say, let me see, blue pen. So minus 8.5 minus 0.1n over the square root of 0.09n must be equal to 0.50. So just to make life easy, just put the minus sign on the other side. So cross this minus sign and put it here, just to make the maths easy. Multiply this fraction across, so the bottom term, so we have 8.5 minus 0.1n equals minus 0.50, and then root 0.09n. Just to make your life easy as well, just partition this one so it looks a bit like root 0.09 times root n. So you can do that with surds, and just multiply that head on, the surd part, with minus 0.50, and you guys should get 0.09 minus 0.15. So all of this becomes minus 0.15 root n. Okay, and what do we do from here? So this is not very obvious to tell, but you would have to kind of, this actually becomes a quadratic equation. How do we know? So we got n and root n. If we just say on the side, yeah, you know, let x equal root n, if you square both sides, you have x squared equals n. So it's putting that back in, we have something like 8.5 minus 0.1 x squared, because n is x squared, minus 0.15 x. And voila, guys, here's a quadratic. So now rearranging this to the usual format. So let's put it down here for a second. So we should have, let me see. So let's plus 0.1 squared across and subtract 8.5. So we should have 0.1x squared minus 0.15x minus 8.5. Yep, looks okay. Yeah, and then just using the quadratic formula, so I've already gone ahead and solved it anyway. And using the quadratic formula, you should have exactly, so yeah, just to be clear, it should be minus b plus minus square root of b squared minus 4ac. Standard procedure, where a is 0.1, b is minus 0.15, and c is minus 8.5. Plugins in the calculator, you should get about 10. Ignore the negative answer, because you want a whole value. Or you should have another answer, but stick with the 10. And then squaring this, you should eventually get x squared, which is of course 100. And yeah, and that's it. And then since x squared is 100, well, n is clearly 102, since x squared is n. And that's it, guys. So the continuous random variable x has the following PDF. Now, for part A and B, they want us to firstly sketch this graph and then find the value of k, which is, as you can see, is multiplied to everything. And one thing to note, when you look at all this equation, we need to see that all of these are just examples of straight lines, okay? And sometimes the k can be kind of annoying. So what I personally do, I would rewrite all of this as fx equals k times and then everything else. X minus 2, and then that's just going to be 1, and 6 minus x. And that's it, and they all have the, you know, the same ranges. So that's the basic bit. Now, what do we do from here? So to sketch this, well, let's just go ahead and sketch it from what they want from the intervals. So get your xy graph out and just plot a couple points. Just plot up to, on the x-axis, from 0 all the way to 6. So this could be 1, 2, 3, 4, 5, 6. And just be very careful when you see the ranges, because this is where we want them to be. So let's see. So according to this one, we want x minus 2. So let's just label this out. So we want firstly from 2 to 3. Now what do we have? We can say when x equals 2, we get 0. So it should be on the line. Let me change the red actually. When we get x equals 3, it should be 3 take away 2, which is 1. So technically it will be up here. Let's just say 1, for the sake of it, would be k. So in other words, we get 1 times k, which is k. Now moving on, so yeah, this is a straight line connecting. So now we're going to move on to 3 to 5. This appears to be a straight line of 1 or k. So this is just a straight line going all the way to 5. So that's quite easy. Now let's have a look at the last one. So this is 6 minus x. So we can say when x is 5, we get 6 minus 5, which is 1. So 1 times k is k. So that's fine. So same place. When you put 6, you get 0. And that's it, guys. That's literally it. You literally get a shape of a trapezium. Now, yeah, a lot easier than it looks. Now for part B, show that the value k is a third. One thing to know about these kind of shapes is that the area underneath the curve or the line is always going to have a total area of 1. So just look at the shape. This is just a nice little trapezium. And it's got firstly a width, so it's up to 6, 2 to 6, so it's got a width of exactly 4 across, and another width at the top of 2, and yeah, and it's got a vertical height of k. And we know straight away that the area equals 1. So using the area of a trapezium, which is actually half a plus b, so the average of these two lengths times the vertical height, this will give us the area, and the area is 1. So go ahead guys, just literally smashing the values. So we have firstly half, and then inside we have 2 plus 4, so it'll be half times 2 plus 4. And the height is k, and it must equal 1. And well, smashing this in your calculator, you get 6 over here. Half of 6 is 3, so 3k, and hence k must be a third. And that's it guys. A and B has been solved. Okay guys, here we go, part C. Now we need to define fully the cumulative distribution function fx. Whew, this one's the worst of them all. The key idea here is that we need to pretty much accumulate as we go. So let's just go ahead and put the obvious points. At some point, up until x2, so x value is less than 2, we should have nothing accumulated. Whereas once we get to x equals 6, all the properties would have accumulated to 1. So this is already the initial conditions, yeah? Now, how about the rest in between? Well, we just need to integrate, and then for the layer one, just add the previous terms. So let's just have a go, yeah? So watch me do this. So for the very first one, let's integrate this one from 2 to x. Why x? Because that is the definition of cumulative function. We need something in terms of x. So let's see. So I'm going to call this one a, yeah? This will be the first one. So we're going to do a, b, and c. And I'm going to put a, b, c here respectively too, yeah? So for a, let's just integrate that. So we're going to integrate from k from 2 to x of x minus 2 dx. And I've already gone ahead and integrate this, so you guys, I'm guessing, should get the following. And remember, k is 1 over 3, yeah? So doing this, you guys should get 1 over 6 x minus 2 all factorized. So this is my factorized expression. You get something similar, but it's fine. Now, that is literally done for that. And this is from the limits as given. So we can just say a here is 1 over 6 x minus 2 squared from the given limits, yeah? You could do it anyway, but I'm just going to write like this because it's quicker. Okay, now we do the second part. So let's integrate k, yeah, from 3 to x. So same story above. And oh yeah, for this one, we also need to add the previous term. So we can say integrate from 3 to x of k, plus we also add the value from a. And remember, in this case, we're accumulating, so we need to add from the limits 2 to 3, not 2 to x. Okay? So literally just plug in x equals 3 here, and equals 2 there, and you get a result. Anyway, doing this, what happens? So integrating k with respect to this, you guys should come up with a result like kx and then minus 3k. And then at this point, we just add the values of this one. So when you plug in 3 and 2 to the a equation, you should get 1 over 6. And lastly, just tidying all this up and replacing k with its true value of 1/3. I just do this because it's easy work k. You should get x over 3 minus 5 over 6. Remember, this video is only about, at least this question is only about showing you how to do it, not evaluating every integral, because, God, that is long. Now, as for the third part, C, so this interval here, we do the same thing from 5 to x, and of course, add the previous 2 terms now. So let's do it. Integrate from 5 to x of k 6 minus x. So you can put k outside as well. And then 6 minus x dx. And of course, adding the 2 previous terms from a, 3 to 2 plus b, from, what was the limits again? 3 to 5, yep. So again, plugging in 3 to 2 for a and 5 to 3 for b, we should get the following. So evaluate the first integral, guys, and you guys should get simplified one. So 6x minus x squared over 2, and then I'm plugging in as we go here, minus 35 over 2k when you plug in 5. Now this is the first integral. Now as for a, when you plug in the values for a, you should get 1 over 6 because we know that. And as for b, when you plug in the values for 5 and 3 into this b equation, it should reduce to 2/3. And now the final result. So tidying all this up and putting k to your original value, this first term becomes 1/3 of 6x minus x squared over 2. All of this chunk over here with the right value k will give you just a nice minus 5. And that's it, guys. Whew, and we're done. Now all you do is just throw this back into the equation. So let's see, b is x over 3 minus 5 over 6. For x values, you know what, for basically these x values, yeah, between 3 and 5, I use curly brackets to indicate that it's less than or between. I use the square bracket to indicate that it includes the values. Okay, just for your exam, best to use the notation that you have, yeah. For c, same thing, so it'll be all of that, 1/3 6x minus x squared, 1/3 6x minus x squared over 2, minus 5, and that's it, all done with the same limits as above. Whew, not easy. Okay, finally, now let's look at part D. Hence, find the 90th percentile of the distribution. Well, this one is very easy. We're literally trying to find the value of the cumulative distribution at the point x when it equals 90%. Now, looking at the 90th percentile, this is pretty much the top 90% near the end of the tail. And looking at this one here, if I had to guess, the 90 falls in end, so it's probably somewhere between 5 to 6. Just to be on the safe side, yeah? The mean will be probably between 3 to 5, or actually, it will be. Because this is a trapezium. It's bang in the center. And it's got equal lengths. So yeah, it has to be between 5 to 6. So this means that this cumulative distribution, we can literally just plug in a value. So using, of course, the cumulative, not the density, my bad. Plug in a value for, just solve for x, literally, and equate this equation to 90%. So what do we have? So now we have 1/3 6x minus x squared over 2. So the cumulative distribution for C must equal 90% or 0.90. Okay, and now subtracting across, oh god, and expanding all of this, let's have a look. Expanding this, you should get 2x minus x squared over 6. Subtracting this across, we're going to have minus 5.9. All right, yep, looks good, equals 0. Now rewriting this to the standard quadratic form, you should have, so moving everything to the right hand side, you should have a positive x squared over 6 minus 2x plus 5.9, and yep, we're pretty much done. So to solve this, just use a quadratic equation and you're done. So using the fact that x equals minus b plus minus b squared minus 4ac all over 2a, where a is 1 over 6, b is minus 2, c is 5.9, then, just checking if it's okay, then you just plug in. When you do this in the calculator, you should get two results. Firstly, 5.23 or 6.77. Which one's the correct one? Well, let's go ahead and look at our distribution. We know that x is between 5 to 6. Otherwise, it should be 0. So technically, this second answer does not belong, because if you get over 6, then the answer should be 0, but that's not true. So the only respectable value is this. And that's it. And now finally, guys, let's move on to part E. So here we need to find the probability that x falls between the mean and 5.5. This would be so easy if it wasn't for EX, because we have the cumulative distribution and you just plug in f 5.5 minus f whatever the mean value is. So before we do this, let's find the mean. Right. So thankfully the mean is actually really easy now that I think about it. Remember the sketch we did in part A? It looked a bit like this. So it was just simply a trapezium, and we know it hits at 2, and this part was 3, and this part was 5 because I'm looking at the limits, and this part was 6. So it's actually symmetrical. So because a certain shape is symmetrical and it's pretty uniform, at least in most parts, we can literally slice it through the middle, and then hence this would be the perfect mean. So the mean here is between 3 and 5. And yeah, so 3 plus 5, and yeah, it's literally the midpoint, so it has to be 4. So then EX is 4. So if you're wondering how this result came about, well, they just used the graph. Alternatively, you could be really long about this and integrate every single term, but that would be a very long process and you don't want to be doing that. Anyway, solving this problem head on. So EX is 4. Now we could just plug in 4 there. So we're going to have now the probability that 4 is between, X is between 4 and 5.5. Oh man, it's been a long day. So solving this one, you just literally say this is the same as F 5.5 minus F4. So literally find the two relevant ones from the fx. So using the cumulative distribution function, 5.5 lies between 5 and 6. So again, this is for 5 and 6. So we pick this one here. Let me just highlight. So we pick this one and replace this value with 5.5. And then for the second one, F4, you use the B distribution and you place this with 4. And doing so, you should get an ultimate final result of 11 over 24. Voila. All done, guys. All done. Whew. Well, thank you. Anyway, I just want to say thank you for watching my video, and well, I shall see you soon. Ciao.